All right, so today we're going to talk about alternating series. A lot of the series we've talked about so far have only had positive terms. We've talked about alternating sequences, right? Sequences whose terms alternate back and forth, but we haven't added them up to be a series yet. So, the most common way we see alternating series are in either one of these forms. The only difference is which terms are going to be odd or even. Here, when n is equal to 1, we end up with a negative number, so the odd terms are negative because whenever the power is odd, you'll have negative, but then up here, when n is equal to 1, you have negative 1 to the n plus 1, so it'll be negative 1 squared. So now that makes the first term positive, and then the even terms will be negative because you'll add 1 to that power. So that's the only difference, is just which terms are positive or negative. And so that's all you need to be an alternating series. But they're a little bit more tricky to determine whether they're converging or diverging. So if we're going to determine if an alternating series is converging or diverging, 1, it has to be alternating. And 2, we want to see if the limit of a sub n is equal to 0. And the a sub n is just the part that's without the alternating part. Like, you don't need to do the limit of this part, just the part without the alternating part. Okay? So that's what a sub n is in the alternating form. If that limit is equal to 0, and if a sub n plus 1 is less than or equal to a sub n, so what this really means is just that the next term, a sub n plus 1, is less than or equal to the previous term. Right? So you might see this as non-increasing. What does non-increasing mean? That means decreasing or just staying the same. Because this says that the next term is less than or equal to, it could equal the term before it, an. Okay? So, one thing to also note is, what if you have an alternating series and you are checking the criteria and the first one doesn't apply? What then? Well, in general, you can't use the alternating series test if the first criteria doesn't apply. You have to have both of them to use the alternating series test. But the nice thing is that when the limit as n approaches infinity of a sub n is not 0, this means that the limit as n approaches infinity of negative 1 to the n of a sub n will not be 0, because add the alternating part in and that limit will still not be 0. And so then you will be immediately able to say that the series diverges by the nth term test. Because that's the nth term test. If the limit of the series is not 0, then it diverges. What if the second condition is not met? Well, we'll address a few different situations like that, but you can't use it if they're not met. So you need both of them to be the same. So let's look at 2 examples here where we'll use the alternating series test. So we can tell that this is an alternating series because of this part. The part that we care about for the alternating series test, an, we're just going to call 1 over n, right? So an does not include the alternating part, all right? But it is alternating, it's an alternating series. So if we want to test if this alternating series is converging, we're going to first take the limit of just the an part and see if it equals 0, which it does. So that part, check. And then we want to see if it is decreasing or staying the same or non-increasing. So we want to see if a sub n plus 1 is less than or equal to an. That's our goal, right? So we want to compare a sub n plus 1, and we want to compare an. Well, an is just 1 over n, and a sub n plus 1 is plugging n plus 1 in for n, right? So that'll be 1 over n plus 1. So like if this is 1 over 3, then this is 1 over 4, right? The next term. So a sub n plus 1 is just the next term. And now this is actually really easy to compare because what happens here, n plus 1 is going to be bigger than n, right? Because it's the next term. And so the denominator over here is bigger than the denominator over here, which means that the fraction is smaller than this fraction. And that's exactly what we wanted to show. We wanted to show that a sub n plus 1 is less than or equal to a sub n. So this right here shows that this is true. So this is our second part. So then we would just say that the series converges by the alternating series test. Okay, so let's do another example. This guy over here, this is clearly an alternating series because this part here tells us that. This is a sub n. So first we will take the limit as n approaches infinity of the a sub n part. These have the same degree, so they're growing at about the same rate. So we'll look at the ratio of the leading coefficients for the limit. So that will be 1 over 1, which is just 1. So this is not 0. So not only can we not continue to use the alternating series test, but the fact that the first condition is not met, because the limit as n approaches infinity of this is 1, then the limit is not 0, then the limit as n approaches infinity of negative 1 to the n of n over n plus 1 will not be equal to 0 as well. It'll alternate back and forth between positive and negative 1. So this is exactly the nth term test. So we would say the series diverges by the nth term test. In a second here, I'll address what happens if it doesn't meet the second criteria. But for now, I want to talk a little bit more about how to show that a series is non-increasing or decreasing, okay? So we just showed that by showing that a sub n plus 1 is less than or equal to a sub n. So this shows non-increasing, the second part. So this is this method right here. So if you want to verify non-increasing behavior for a sequence, you can show that the algebraic difference here between these two things is less than or equal to 0, which that is equivalent to this statement right here. Because if you subtract an over to this side, then you have this statement, right? So this is one way to show that we have non-increasing behavior. Another way to show non-increasing behavior is to find the derivative of the related function and show that the derivative is less than or equal to 0. That's what we did with the integral test, right? So sometimes you'll see people with the integral test, instead of showing that the derivative is negative, they'll do this method showing that the next term is smaller than the previous term, even with the integral test. And then the other way you can do it, which sometimes is easier if this is just too complicated to compare these two terms, is you can show that the algebraic ratio here between the next term and the term before is less than or equal to 1. So if you take the next term divided by the previous term, and that's less than 1, then that means the next term is getting smaller, right? Like if you have a sequence that says 2, 3, 5, right? If we do 7, 12. If I do 12 divided by 7, that's going to be bigger than 1 because it's increasing. But if I do a sequence that is decreasing, we'll do something as basic as 10, 9, 8, 7, 6, ... So the next term, like if we choose 8, right, the term before that, then that's going to be less than 1. So just to help you kind of understand what that symbol means. So let's show an example where this algebraic ratio method might be helpful. Okay, and you can do any of these anytime. It's all personal preference. I tend to stick to this one up here, but it just kind of depends on the problem. So let's take a look at this example. We can see this is an alternating series here because of this part. So this part is going to be the a sub n. So a sub n is going to be 1 over 2n factorial. Comparing a sub n plus 1 and a sub n might be a little tricky here. So we're going to not do that method. We're going to do the limit as n approaches infinity of a sub n plus 1 over a sub n. And so a sub n is just this guy right here. And then a sub n plus 1 means you put n plus 1 in here where the n is. So we'll do 1 over, get this out of the way. We'll do 1 over 2 times n plus 1, and that's all factorial. So first, let's flip and multiply. So we'll have the limit as n approaches infinity of 1 over 2n plus 2. I'm going to go ahead and distribute here the 2. And then times 2 to the n factorial over 1. So this will be the limit as n approaches infinity of 2n factorial over 2n plus 2 factorial. And a cool thing about factorials, and this will come into play a lot later, is that factorials cancel out a lot. So we'll look at a quick example here. If I have 15 factorial over 10 factorial. Remember that 15 is 15 times 14 times 13 times 12 times 10 times 9 times 8 times 7, dot, 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 dot. 10 factorial is 10 times 9 times 8 times 7, dot, 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 dot. So when I'm dividing these two things, this 10 times 9 times 8 factorial will cancel with this part of that factorial, and you'll just be left with this part here in the top of the fraction. So whenever you have factorials like this, you just need to write out a couple of the first few terms. So we'll do the limit as n approaches infinity. And like the first number of this top factorial will be 2n. And then the next number will be 2n minus 1. And then the next number will be 2n minus 2, dot, 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 dot. Because you just subtract 1 each time you go down, right, when you multiply. Then the bottom factorial, the first term, will be 2n plus 2. The next one will be subtract 1 from that, 2n plus 1. Subtract 1 from that, and you get 2n. Subtract 1 from that, and you get 2n minus 1. Subtract 1 from that, and you get 2n minus 2. And we could keep going, right? But what you can see here is you can see where they start to cancel out, because this 2n will cancel out with all of this. So then all we'll be left with is the limit as n approaches infinity of 1 over 2n plus 2 times 2n plus 1. And that limit's really easy because the n's only in the denominator, so as we plug in infinity into the denominator, that will be equal to 0. So this example here was just to show a slightly different way to show non-increasing. So let's backtrack to the beginning for a minute because we didn't really do the alternating series test. So the alternating series test first says we have to start by showing that the limit as n approaches infinity of a sub n, remember that was just this, that equals 0, which that obviously equals 0 because as n grows in the bottom, that will be 0. And then step 2 was what we just did right here. We showed that the limit as n approaches infinity of a sub n plus 1 over a sub n is less than or equal to 1. this part here. So it's just another different way to show that it's non-increasing. So this is part 2. We showed that that limit was less than or equal to 1, so that shows that that's non-increasing. So this definitely series converges. Okay, so these examples here on the next page are just some examples of what I was talking about earlier, that you have to make sure you check both parts of the alternating series test, because you can have some series where it meets one criteria but not the other criteria. Like these first 2 examples here, they have the limit as n approaches infinity, but they're not decreasing. One diverges and one converges. So you can't use the alternating series test to test convergence if one of the criteria are not met. And then you have another example down here at the bottom. But like for this example right here, this is an alternating series, but it's really right here, you've got 2 geometric series subtracted together. And if you have the sum or difference of 2 convergent series, then you can just conclude that the 2 series converges. We had a kind of a practice problem like that in class. So that's totally legally when you have 2 series added or subtracted together. If one converges, then they both converge. If one diverges, though, then they both diverge. Okay, so now we need to talk about something that's pretty important. It will come up a few times, and this is the alternating series remainder. And this is pretty cool, but there's some notation we need to discuss. So the alternating series remainder theorem says that as long as we have a convergent alternating series that is non-increasing, you can think about it as decreasing as well. Just realize it's decreasing, or it could stay the same. Then the value of the remainder, Rn, involved in approximating the sum is less than or equal to the first neglected term. So this is a lot of words. So what does this mean? So this big S right here, this is the actual sum of the series. And this S sub n is a partial sum. So this is the sum of the first n terms. So this is an approximation of the sum, right? So maybe we say that the actual sum of the series is S, and then let's say we add up the first 100 terms of the series to try to approximate what the actual sum of the series is. And if we take the difference between those 2 values, so 100 terms is a lot, so hopefully we would get pretty close to approximating the sum if we did 100 terms. So the difference between the actual sum and this should be a pretty small number, right? And so that is what we call the remainder, right? It's going to be the remainder, or the error, right? And what this says is, this is actually pretty cool. This says that this error, whenever you use any number of terms to approximate, this error is always going to be less than or equal to what we call the first neglected term, so the next term. So this will be less than or equal to the 101th term itself, the actual value of the 101th term. We're all talking absolute values here because positive and negatives and errors don't really matter. So let's look at an example of this. Okay, so this says approximate the sum of the following series by the first 6 terms. So we're going to add up the first 6 terms. That will be S sub 6. So we have them here already listed out for us. These are factorials. So 1 over 1 factorial is just 1. 1 over 2 factorial is just 2. 1 over 3 factorial is 6. 3 times 2 times 1. 1 over 4 factorial is 4 times 3 times 2 times 1, or 24. 5 factorial is 120. 6 factorial is 1 over 720. And if we add all of those up, we will get the fraction 91 over 144. And I'll go ahead and tell you that's 0.63194. Okay, so this is an approximation of this sum, because this sum is infinite, right? But stopping at any value is an approximation. So then if we want to know how accurate that is, right, how close to the actual sum that is, we want to look at the next term, right? So we are going to look here. That would be a sub 7. So we're going to look at the next term when n is equal to 7. Because we started with 1, 2, 3, 4, 5, 6 terms. The next one will be when n equals 7. So that'll be negative 1 to the 8th times 1 over 7 factorial, which will be about, it's like 0.00198, but we'll go ahead and round to 0.002. Okay, so now this term is our remainder, our error between the actual sum s and this approximation s sub 6, or 91 over 144, is going to be less than or equal to 0.0002, right? So the error between the actual sum and this approximation has to be less than 0.0002. So that what that means is we can give an interval for an actual sum by taking our 91 over 144 and add this amount to that and then subtract it, and we know that our sum has to be between those two values. And if you do that with the actual values, we will get that our actual sum has to be between 0.63214 and 0.63174. Because the difference between this approximation and the actual sum is going to be less than or equal to 0.002. So we know it has to be within that amount. Okay, so now let's look at another similar type of question here. And we might sometimes want to know, okay, how many terms do we need to use to approximate the sum with a particular error? Okay, so in this case, we're going to look at our error being less than 0.001. Some sums get really, really small really fast, so you may only need a few terms. Some take a long time to get there, so you may need a lot. And I think it's kind of helpful to, like, you could always try this by hand, right? Because if we want our sum to be less than 0.001, what that theorem above tells us that the a sub n plus 1 term needs to be less than or equal to 0.00, will always be less than or equal to 0.001. So whatever term we find that is finally less than 0.001, then that term, we can add up all the previous terms. So for example, like if we say, let's see the 5th term, right? So that will be negative 1 to the 6th over 5 squared, or 1 over 25, which as a decimal, 1 over 25 is 0.04. So that's clearly not small enough. So we could go bigger. Let's try SA20. So that will be negative 1 to the 21st over 20 squared. So that will be negative 1 over 400. So that will be negative 0.0025. So we're getting closer, right? If we try a 30, we'll get negative 1 to the 31st over 30 squared. So that will be negative 1 over 900. And that's 0.00011. So we're almost less than 0.001. So let's try a 31. That'll be negative 1 to the 32 over 32 squared, or so 31 squared. And that will be 1 over 961. Which is 0.0010. So that's not quite small enough. So if we go A32, we'll get negative 1 to the 33 over 32 squared, which will be 0.0009 finally, and we'll finally get less than that error of 0.001. So when we get to the term 32, the error, that value of that term itself is less than 0.001. So then if you add up all the previous terms up to 31, and you add all those up, that error will be less than this, right? The next term, okay? Now, this is super time consuming, right? Just guessing here, seeing how far we go. So this is probably not going to be the most useful method for this, but I want you to kind of understand what we're doing. So now, another method to see what it is, because what if you need to go to 1,000 terms or 500 terms or something like that? You're not going to be guessing all of these values. So what can we actually do then? What we can do then is say, okay, we need the a sub n plus 1 term to be less than 0.001, because if it's less than 0.001, then we will be good to go. And so a sub n plus 1 will be plugging in n plus 1 in here, because remember, a sub n here is just 1 over n squared, okay? So we'll plug in n plus 1 in there, and so we'll have 1 over n plus 1 squared, and we want that to be less than 0.001, which that's the same thing as 1 over 1,000. Then I'll multiply by 1,000 on this side, multiply by n plus 1 on this side, and try to solve this inequality. Take the square root of both sides, square root of 1,000, and then subtract 1, and we'll have the square root of 1,000 minus 1 will be less than n. And if we do the square root of 1,000 minus 1, we get 30.6227 is less than n. So n needs to be bigger than 30 point blah, 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 blah. So n can be, well, 31 will be the next whole number bigger than that. So we need to use the first 31 terms to approximate the sum. And if you add up the first 31 terms, then the 32nd term here, that will be less than 0.0001. And so then we know that our error will be less than that because of our theorem. So let's look at one more quick example here. We're not going to do this one from scratch because obviously that's too much work, but I wanted you to see what was happening here. So here we're going to see what a n plus 1 is, and we want that to be less than 0.001, same error. So now if we plug in, and remember a n here is just 1 over 2 to the n times n factorial. So plug in n plus 1, and we'll have 1 over 2 to the n plus 1 times n plus 1 factorial is less than 0.001. And here you might be thinking, oh, dang, how the heck am I supposed to solve an equation with a factorial in it? Well, you don't need to. Yes, I agree. That would be very, very difficult. So let's just make it look a little more reasonable. So we'll make this 2 to the n plus 1 times n plus 1 factorial is less than 1 over 1,000. Multiply by 1,000. Multiply by the denominator over here. Just so we can kind of read it a little bit better. And another option sometimes is just to kind of guess and check what we were doing, but this is going to be a little faster guess and check here. So like if we say, okay, what if we do n equals 3, right? Will that make our value less than 1,000? So here's the question here. 2 to the 4 times 4 factorial, that will be 16 times 24, and 16 times 24 is 384. So is that less than 1,000? Or is that greater than 1,000? No. Right? That is not greater than 1,000. So 3 doesn't work. But let's look at what happens with 4, because factorials go up really fast. So the question is that greater than 1,000? So we'll have 2 to the 5th times 5 factorial, and that will be 32 times 120, which is 3,840, which is greater than 1,000. So we need to add up the first 4 terms. And then our error will be less than 1/1000 because the next term, the 5th term, will be less than 0.001.